I was saying how I needed to show you guys um, why the implicit differentiation, but with like conceptually using derivative like fractions, and I figured out a way to do it. So let me
Wait,
show you guys.
derivation? A derivation?
I mean, it's not a derivation, but I figured out a way to show it using fractions, like
Oh,
fractions of derivative.
okay.
Um, okay. Can you guys see my screen?
Yeah.
Okay, so let's say we want to find uh let's say we want to find the derivative of uh of y squared, right? So what we want to do is let's set that equal to a variable u. And do you agree with me that du dx is equal to uh
2y, y prime. Wait, no.
dy dx?
Yeah.
So that means if we find du dx, we find dy dx. And to find du dx, we do dy oops, not dy. We do du dx times dx dy. Is that right? No, no. Whoops. Du dy times dy dx. Oops. Shoot. Dy dx. And if those cancel out, and you get du dx, right? So what's du dy? What's the derivative of u with respect to y? If we treated y like our variable that we're differentiating. Does anyone know?
2y, prime.
It would just be 2y because we're differentiating with respect
Oh,
to y.
yeah.
Not
2y,
we're
yeah.
not differentiating with respect to x or any other variable.
X. Got it.
So it would be 2y times dy dx. So that's why the derivative of y with respect to x of y squared is equal to 2y times dy dx. Um okay. So that's that conceptually. Now we can get on to whatever you guys are learning now. So what have you guys been doing?
Newton's approximation, local linearization, and then I think that's pretty it.
Okay, well,
Differentials too.
okay, different. So so differentials, uh, Newton's approximation, and what was the other one? Local linearization.
Local linearization.
Okay.
And then we got inverse trig derivatives as well.
Oh,
And
okay, nice,
implicit,
nice.
which
And
goes with
implicit.
pretty much everything.
Okay, I think I
Yeah.
talked about implicit last week. So
Yeah.
if you guys wanna learn more about that, you can see the video that I put in the section on the Discord. So we'll just do these for now. Let's start with, I think inverse is probably, actually, yeah, let's do inverse right now. So let's say uh let's say we want to find the inverse derivative, or not the inverse. Well, let's say we want to find the derivative of sine x, right? Or sine x is equal to y, and we want dy dx, right? So, and we don't know what the derivative of this is with respect to y. Well, we can manipulate it so that we take the sine of both sides, and we say x is equal to sine y, right? So if, and what is sine, right? Sine is a function where you plug in an angle and you get a ratio. So that means there's a triangle with angle y that the ratio of opposite over hypotenuse is x. Opposite over hypotenuse is, what's opposite over hypotenuse? X1. And this is a right triangle, so what do we know that this side is?
One minus a squared.
One minus
squared.
x squared.
Yeah, so now we can take the derivative of this with respect to what?
D over dx.
Yeah, we want to find d over dx of both sides. And since we know our implicit differentiation, we know that this, so what's the derivative of x with respect to x. That's 1, right? And then we know that this implicitly is cosine y times dy dx. And since we know that our original function is based off of this ratio, the derivative is also based off of this ratio. So cosine y is what? Square root 1 minus x squared times dy dx. And that's equal to 1. So dy dx is equal to 1 over square root 1 minus x squared. And pretty much all the problems go like this. So I probably, unless there's one that's really tripping you guys up, unless there's one that's really tripping you guys up, I'm not going to do more of these because they're all kind of the same. But does that make sense? What you're doing is you're manipulating the function, right, so that you can implicitly differentiate and explicitly differentiate both sides. And then, since this is a trig function, you can make a ratio based off of the original function, which means you can plug that ratio back into the derivative. Does that make sense?
Yeah.
Yeah.
I had a question.
Uh-huh.
For like the inverse trig. There was one question. It was like y is equal to sec inverse square root x.
Wait, could you repeat that?
Y is equal to sec inverse root x.
Okay, wait, could you guys give me 1 second? I'm gonna stop sharing and then share real quick. It'll just be like real quick. Okay. All right, you guys can see my
Hey,
face, right?
Sid, can you add Avi in real quick?
I think I did.
Oh, you did. Okay.
Yeah. Okay. So we want to find what? Well, could you say that again, Tremont?
Yeah. Y is equal to
Okay. Y is equal to
sec inverse.
secant.
Yeah, secant inverse square root x.
Okay. Well, we take the secant of both sides, right? And it's square root x. And also keep in mind, if you're ever trying to find y, like it asks you for the value of y in the derivative or anything, right? Keep in mind that this has a domain restriction. I can't think of a problem where we'll have to do that, but if a problem ever comes up where it's like find y when x is this in the derivative or anything, you have to keep in mind that domain restriction. So anyways, okay, so we take the secant of both sides, then we take the derivative with respect to x on both sides. The derivative with respect to x we do implicitly here. It is secant y times tangent y times dy dx is equal to, well, this is x to the 1/2, so it's 1 over x to the 1, or 1 over 2x to the 1/2. So we know that, and actually I'm going to rewrite that as square root x, just because we're going to turn this into a triangle. So when we turn this into a triangle, right, we know that secant y times tangent y, we can turn that into, oh, you know what we're supposed to do? Wait, give me 1 second to think about this. Secant inverse of root x, right? Secant y times tangent y. Can we turn this into, okay, so actually, since I see what the problem is here, because we can't turn this into a triangle because there's secant and tangent on both sides. So what we need to do is, do you agree that, this is also, this? I think this works. Let me see. Secant, cosine inverse root x. I think those are the same, right? We can agree on that. So we can say that cosine inverse of root x is equal to 1 over y. Then we take the derivative of both sides implicitly, and we get, on this side we get, oh wait, we can't take, oops. Oh shoot. Okay, wait. Do you guys remember how to do this? I'm actually struggling a little.
Well,
I
when
tried
you
drawing
just
a triangle.
yeah
The hypotenuse is root x. The
Yeah.
opposite leg is
Yeah,
root
you
x
know why?
minus one.
I pressed this again. Yeah, I took the derivative and then tried making a triangle out of it. I knew I was doing something wrong. Yeah. So you first take the secant of both sides and then make the triangle. I don't know what I was
Yeah.
doing.
yeah.
Yeah.
So you get secant y is equal to
I have
root
no
x,
clue what
and
I
then
was
the
doing.
triangle is root x is the
Okay.
hypotenuse.
Yeah.
The opposite leg is root x minus one, and then the other leg is one.
Okay, makes sense. Give me 1 second. Where's the undo button? Oh, it's down here. Okay. So secant y, yeah, I don't know what I was doing, is equal to root x, right? So that means
Yeah.
secant is secant's what? What is secant? 1 over cosine, so that's hypotenuse over adjacent. So square root x over 1. So this side is square root of the square root of x squared, which is x minus 1. And you do this with the Pythagorean theorem. So you do that, and then you take the derivative. Yeah, I don't know what the heck I was doing. Boom, tangent y dy dx is equal to 1 over 2 square root x. So secant y we know is square root x. We can look at the triangle or we can look at the original function. And I'm gonna switch my work to up here once I write this out because there's not enough space. Secant y, tangent y. What is tangent y?
You mean cotangent?
No,
Oh, you take
tangent.
tangent one.
Opposite
Square root
over.
of x minus one.
Yeah, it doesn't matter how you set up your triangle. If you can, you can. What was I gonna say? You can turn this into cosine and set up the triangle like that. Does the same thing. But anyways, shoot. Tangent y is opposite over adjacent, so square root x minus 1. There we go. Times dy dx is equal to 1 over 2 square root x. So what do we want to do now? We want to divide by these on both sides. So we get dy dx is equal to 1 over 2 times square root x times square root x times square root x minus 1. And then that becomes 1 over 2x square root x minus 1. I think that's right. That should be right. Is that correct? Okay. Then, is there any more questions on... Wish I could move this. But anyways, is there any more questions on inverse trig? It's all kind of the same.
Wait, why do I get a different answer if I do cosine cotangent?
If you do cosine instead,
Yeah,
You
cotangent.
get the same thing. You get the same thing. You just have to move it on the other side. So then you get y prime is equal to 1 over 2 root x times cosine y cotangent y. It's the same thing what just happened here.
it's
Okay.
okay. Here's how you do it in terms of inverse cosine. You have to actually switch the ratio inside. You don't put it all 1 over the same thing. So cosine 1 over root x. Is that what you did?
Yeah, well, I mean, actually later on, like where you had secant y times tangent y times dy dx is equal to 1 over 2 root x. I switched to secant x and tangent y, moved that to the other side. So I had dy dx is equal to
Yeah.
cosine y times cotangent y.
Okay, so
times-
what's cosine y? So that would be 1 over 2 root x times cosine, which is 1 over root x.
Oh my god, okay, I understand where I messed up. Never mind.
A
Okay.
question popped up in the chat if you want to check it out.
Oh, okay. Let me see it. Homework help? Or
No, this Zoom meeting chat.
Zoom meeting? Okay. Can you do f of x is equal to arc cosine x plus arc sine x? Okay, cool. We can do that. I'm gonna erase all of this. Could someone keep in mind what we're trying to do? Come on, where's the eraser? There it is. Okay. So what do we want to do exactly? We want to do... Shoot, let me erase all this. We want to do the... So y is equal to our cosine. So cosine inverse of x plus sine inverse x. Okay, so I think the best way to do this is using the chain rule. So we find cosine inverse, and then we do the derivative of the inside, and we multiply them both, instead of trying to do this by taking the cosine of both sides. So let's do that. So let's say u is equal to cosine inverse of x, right? So cosine u is equal to x. So that's x1 square root of 1 minus x squared. Negative sine u times du dx is equal to 1. Is there a negative there? I feel like I'm doing it wrong. That's right. Yeah, du dx is equal to 1 over negative sine u. So 1 over negative square root 1 minus x squared. Is that the derivative of cosine inverse x? Yeah, I want to do that themselves. Can you guys hear me?
Yeah, seems right.
Oh, okay. All right, cool. So, yeah, I don't remember there being a negative there, but maybe it's just because I haven't done this in a while. Okay, so that's cosine inverse, right? So, oops. Yeah, I'll put the negative 1 on the top. 1 minus the inside, because we're doing chain rule, x plus sine inverse x squared, okay, times the derivative of this, and that's 1 plus the derivative of sine inverse x. Okay, so the derivative of sine inverse x is, let's say a is equal to sine inverse x. So sine a is equal to x. So we make a triangle, a x1 square root 1 minus x squared. I'm doing this in my head just because I don't. You shouldn't be doing this stuff in your head, but
Sid, can
square-
you just plug in 0 at that point?
plug in 0. We need to multiply it by the derivative of the inside though, right? And then we can.
There's no negative sign for the negative. For the inverse sign, I got 1 over square root of 1 minus x
Yeah,
squared.
that's sine. That's this over here. I think cosine is the one that has the negative. Am I messing up there?
No, I think you're good.
Okay, so then it's 1 over, so times the square root of 1 minus x squared. Okay, so that's the derivative of the outside times the derivative of the inside. So that's the outside, that's the inside. Now we can plug in 0.
Wait, sorry to interrupt you, but someone's waiting in the.
Oh, really? Oh, whoops. Okay, there we go. So dy dx of 0 is negative
I
1.
think you forgot one plus the 1 for like the derivative of x.
Oh, shoot. Yeah, I did. Dang. Okay, there. Okay, so that's what it is. If we plug in 0, that's negative 1 over the square root of, what's sine inverse of 0? What angle gives you sine of what angle gives you 0? 0, right? So 0 plus 0, so it's the square root of 1, times 1 over 1 minus 0, or 1 plus, 1 plus 1 over, let me just rewrite that. 1 plus 1 over 1 minus 0 squared, so that's also 1. So it's negative 1 times 1 plus 1, so negative 2. Is that right? Does it give you the answer for that one?
Yeah.
Is it negative 2?
Yeah.
Okay, cool. Does that make sense? That was a little messy, but
How would you do it if you start by cosining both sides?
you can't.
You can't?
No, not really. Actually, that's interesting. I was thinking you can't, but I'm starting to think that maybe you can. Let me try it.
Wait, so then how did you know that you could do that? Isn't there like a set way to do like you have to like get the how do you know you have to take the derivative of both sides like immediately?
How did I know that it won't work?
Yeah.
I mean, I just thought it wouldn't work. I'm starting to think it might work, but I thought it wouldn't work or it would be more difficult because there's a sine inverse in here, so one of our sides would have sine inverse on it, and I just didn't want to deal with that. So you can always use the chain rule here, but I'm thinking maybe it does work. Let's see. Cosine y is equal to x plus sine inverse x. So we have a triangle. So it's x plus sine. This is the reason I didn't want to make a triangle. Is because there's like sine inverse in the triangle, which isn't. I don't think that's a problem, but it's also just more work when you could just use a chain rule. But 1, and that's a square root. See, it gets really messy, but I think it's okay. Square root of 1 minus x plus sine inverse x squared. Okay, I mean, I'm starting to see elements. I remember our derivative had that, so I'm starting to see elements of the derivative here, but let's keep going. So we take the derivative of both sides, and we get, so we take the derivative of both sides, and we get negative sine y times dy dx is equal to the 1 plus, and then what's the derivative of inverse sine of x? It was like square root of 1 over 1 minus x squared, or something like that. I think that's it. Square root of 1 over square root of 1 minus x squared. And I think this is what Avi was talking about, where you can just plug it in without like taking sine to the other side. So let's just put this in terms of x first, and sine would be the square root of 1 minus x plus sine inverse x squared over 1, and that's if there's a negative sign, times dy dx is equal to 1 plus 1 over square root of 1 minus x squared. It got a little squished there, but I think that's fine. So if we plug in 0 now for x, this becomes, what does that become? Negative 1? Yeah, negative 1 times dy dx is equal to 2. Yeah, so it does work. The only reason I did it with the chain rule instead was I figured it would be a little easier. But honestly, both ways are easy. Okay, does that make sense? Why I chose to do the chain rule first, and then, yeah, does it make sense why you chose to use the chain rule? Both ways work. It's just, I just didn't want to have to deal with this kind of triangle.
Yeah.
Though, honestly, in the end, it was the same level of complexity. Okay, so, okay, so what else did we have to do? Is there any more inverse trig functions? I can get to them at the end as well. All right, let's do Newton's approximation. So the way Newton's approximation works is essentially it's about finding the zero of a function, approximating it, right? Using calculus. That's all we're doing, right? So we have a function, right? That's a terrible function to use. Let's say we have a function, right? Like this. I've never seen a function like this ever, but let's say there's a function like this, right? And we want to find this 0 right here. We want to find what that is, right? Essentially, we'll pick a number that we can easily plug in. Let's say this is 3, right? Okay, I can easily plug in 3 into the derivative and into the original function, so I can get a line here, right? So we got a line, right? Oh, shoot. Let me drop that the line. So we got a tangent line. Now let's say, okay, where does that tangent line hit the x-axis? Let's call that I think it's x1, right? And let's make another tangent line at x1. And you'll see that we keep getting closer and closer. Like if we keep doing that, let's say x2, when we find the tangent line x2, we keep getting closer and closer. We keep flip-flopping back and forth, but getting closer and closer to our 0. So that's how it works. But the problem is, right? Let's say we picked this value over here to plug in. You see how it's not going to work, because now it's going to start flip-flopping over this 0. So you wanna pick a number that you know is close to the 0. Like, what's cosine of pi, right? Let's say we're in like the medieval times and we don't know what pi is, but we know what cosine is, right? Y is equal to cosine x. And we want to know what the 0 of this function is, right? We know cosine of 0 is 0, but we don't know if there's another value. Well, you can say, okay, I've been crunching the numbers, and like, if I do 3, it gets really close to 0. So I'm going to try finding the tangent line at 3 and then doing Newton's approximation. And you'll find pi. If you do it infinitely many times, theoretically you'll find pi. Obviously you won't do it infinitely many times, so you'll get an approximation of pi. But if you chose to say, okay, I'll do 1 or something, right? You'll actually get closer and closer to 0. You'll get closer. And this is probably a good theory question. Honestly, he might give you that as a theory question.
Wait. So could you explain that how it gets closer and closer again on the curve?
Yeah.
Okay.
Let me redraw this function so it's easier to let me draw it the way Mr. Shio drew it, because that's a pretty good drawing. But let's say we have, I don't know, just a function like this, right? So let's say this tangent line is, what does he call this? Or what does he call the 0? Does he call it x0, or what does he call it? Does he just call it I'm just gonna call this a, right? That's our let me actually, alright, actually I won't call it anything, but let's say we try to find that 0, right? We'll do a tangent line. We can't plug this in. We have no clue what it is, but we know, like, okay, when I plug in like 2, right, I get a number that's kind of close to 0. So I feel like if I draw a tangent line at 2, it's not the greatest tangent line, but it'll do, right? So if I draw a tangent line and then I find the 0 of that tangent line, right, I'll call this x1, and then I do the tangent line again, right, but at the 0 of, and honestly it's kind of hard to see because I didn't draw it wide enough, but if I draw the tangent line again and find the 0 of that tangent line, I'll try zooming. Do you see how there's a little bit of space there? Right here. So
how do you draw the second tangent line? Based off what?
You find the 0 of the first tangent line, right? You pick a random number that when you plug it in, it's kind of close to 0, right? You find the tangent line of that, and you find where that tangent line hits the x-axis. That's x1. And then to get the second tangent line, you find the tangent line at x1. Does that make sense?
I'm sorry, but
Here, let me do this. Let me do this one more time. I think I can draw a even better function. I think if I like zoom in near the 0 and draw it really, there's a formula for this. That's probably why you guys are confused. There's a formula to find it, and I'm gonna do that really soon. Shoot, how much time we got? Oh, we got 9 minutes. Okay, all right. When this Zoom call runs out, can one of you? This is gonna be really sketchy, but can one of you, create a Zoom meeting, and then everyone joins that Zoom meeting? Because I don't have Zoom Pro, and we're out in 9 minutes. So I'll do this, and then we'll do that again. Is that fine?
Yeah, I can make one.
Okay, cool. So, let's say I have a function, and I'm gonna draw this. It's gonna be like the slowest growing function in existence, right? And we have a 0, right? Let's call that, I'm not going to call it anything, okay? We have a 0. What we want to do is essentially find the 0 of the function, right? And that's why when he says approximate the square root of 3, or approximate, the square root of 3, or the square root of 9.1, right? You know that a function, let's say y is equal to square root of x. Obviously this isn't y equals square root of x, but let's say it was y equals square root of x. Minus minus 3, right? The 0 of this function is 9. Wait. Yeah. So the 0 of this function, if I plug in 9 for x here, I get 3 minus 3, right? So what I want to do is I want to find, shoot, okay, you know what? I have no clue. Okay, I'm really bad at explanations today, but y is equal to x squared minus 9.1, right? So that means if I plug in the square root of 9.1 here, it becomes 0. Can we all agree on that?
Yeah.
Yeah.
So pretend it keeps going up here. Pretend it's a parabola, right? Let's say this is the square root of 9.1. So, let's say this is the square root of 9.1. Our red marker here, where it hits the x-axis, our function. That's the square root of 9.1. Well, you know that, hey, I can plug in 3 here pretty easily, right? 9 minus 9.1. You can plug that in pretty easily, right? So let's find the tangent line at 3. These are obviously not to scale, but let's say 3 is over here, right? And I'll find the tangent line at 3. I'll just keep using black. So let me find the tangent line at 3. That was a really bad tangent line, but pretend it's a good one, right? We find the tangent line at 3. And then I find where the tangent line hits the x-axis, because that's pretty easy for me to do. It's y equals mx plus b. It's pretty easy to find where this hits the x-axis versus something like this, right? So let's find where that hits the x-axis. Let's call that x1. It's going to be like, I don't know, like 3.0, or it'll be like 3.21 or something like that, right? So it'll hit the x-axis at x equals 1, our first tangent line, right? And then we draw another tangent line at x1, right? And then we find the 0 of that tangent line, and if you zoom in, you can see that it's getting closer. x1 was over here, x2 is closer to our desired value, right? And then we find the tangent line at x2, and honestly, I don't know if I'll be able to make it really thin. We find the tangent line at x2, and we get, that was a really bad tangent line, but stick with me here. And we see it gets even closer to x3. And we call that x3, and we can see that x3 is closer to our 0 than x2, and x2 is closer to our 0 than x1. So every time we do this process of taking the tangent line near our desired value and finding where it hits the x-axis, every time we do that process, we get closer and closer to our desired value. So we're approximating the 0. Does that make sense?
Yeah.
Yeah.
Okay. Is there any questions about that? Because that's basically all Newton's approximation is.
The applications are pretty easy. Is like this we go.
And then I'll derive the formula you guys use. But that's what Newton's approximation essentially is. Does that make sense? I'm gonna erase this. So if
What were you using good theory? Like, what would be a good theory question?
so let's say we have a periodic function. Is it okay if I erase this? Does anyone still need it?
Yeah.
Okay.
You can erase it.
Alright, I'm gonna erase this. We have 5 minutes, so keep that in mind. This will probably, I might be able to derive it as well, but if not, we'll have to create another Zoom meeting. So anyways, we, let's say we have a function like sine. I'll just do an easy one, like sine, right? So we have sine, right? And let's say we want to find this 0 right here. We know that it's pi, but so I'm just going to put it in parentheses pi. But for the sake of argument, let's just say we don't know what it is, right?
Mhm.
Well, I can say, okay, if I plug in sine of 3, and you would do it manually, you'd find a triangle, you'd put 3, 1, and you'd find the angle. Like, you'd literally draw it out perfectly, and then use whatever they're called, protractors, to find the angle. That's what they do back in the day, right? So let's do that, and let's see. And I say, okay, it's kind of close to 0. It's like 0.1. So I think my 0, what I want to find, the red dot, or the red line, or the red marker, I think that's close to 3. So you'll plug in the tangent line. You'll find the tangent line at 3, right? And then you'll keep doing Newton's approximation. And you'll get closer and closer, right? Does that make sense? It's the same as the last thing I showed, right?
Yeah.
Okay. But let's say you don't do that process of saying, okay, what's a number that's close to 0? Or yeah, right? Or okay, how do I say this? Let's say you pick a number like 1 instead, right?
Mhm.
Now if you do Newton's approximation, what's going to happen? Actually, before I draw it out, what's going to happen?
It'll suck
It's gonna go
into the
toward the-
origin.
Which 0 is it going to go to? Is it going to go towards
The origin.
yeah, it's going to go towards this 0. So Newton's approximation isn't going to magically find the 0 that you want. You have to work with it a little bit. So I was saying that might be a good theory question. Is 1 or 3 a better x0 for sine if we wanted to find pi, right?
3.
3 is a better one. 1 wouldn't
Holy,
help you at all.
That's pretty basic though. Like, what?
Yeah, I know, but a lot of people don't like when they're doing the theory tests. They're too focused on like the formulas and stuff to actually understand.
But there are no formulas on the like the theories.
Yeah, I know, but people still fixate on that. People will try and like
No, it's probably because like they know what they know what they're getting to, right? But they
yeah,
don't
and
know
they
like
actually don't know how Newton's approximation works. A lot of people they just memorize the formula and they keep doing that. So what these people will try and do is like, okay, I'll do Newton's approximation for 1 and 3. Let's see which one gets closer to pi, and then they run out of time and they just guess, right?
Mm.
So yeah, it's a little basic. Maybe it's because this one might also seem basic because you know that pi is 3.14, so you know it's probably gonna be 3. But like, let's just for the sake, I was doing that just for the sake of argument. He might give you a graph or something, right? And he says pick an x0 that will help you find. Just draw a point for x0 that will help you find the red marker. And if you pick like over here, he won't give you any points. But if you pick like over here, he will. You know what I'm saying?
Wait, where? Wait,
If you
let me
pick
see
like
your
if you pick
first-
like over here, if your x0 is
Oh.
at this point, obviously that's not gonna work. You're gonna get towards this 0. You know.
Okay.
But if you just
see.
memorize the
Alright.
formula, you won't know why, or you won't be able to
Mhm.
figure that out. So that's that. Let's see if I have enough time to get. No, we have less than 1 minute, so I might even cut out. So, everyone. I mean, you can. Yeah. Who's gonna make the new Zoom meeting? Well, someone make a new Zoom meeting and then send it in Discord.
Yeah, I can do it.
Okay. Cool. All right.
That's a lot of responsibility on your shoulders, Shaman.
All right. I'll stop sharing and I'll end the meeting. Done with that meeting. Okay. I'll do the tutoring quickly. I'll do the tutoring quickly. I'll be there in
At 7 o'clock, so I think what time is it now?
6:31. I'll be there in 20 minutes. Okay, can you guys hear me?
Yeah.
Okay. I actually have to go by 7, so I'm gonna try and speed run everything. What do we have to do? I'm gonna share my screen. Hopefully. Oh, can someone enable screen sharing and someone else tell me what we need to? I'll do Newton's approximation, the formula, and then what do we need to do after that?
Differentials.
Okay, differentials and was
Local
there?
linearization.
Okay, local linearization is just finding the tangent line, right? And then approximating and then plugging in a complicated number into the tangent line instead of the function. Does that make sense? That's all.
Why did they use that term if it's so simple?
It's so tangent line is the tangent line, and local linearization is the process of using the tangent line to approximate a value. That's why it's a separate term. But it's just using the tangent line, that's all.
Right.
One neat trick you can do, let's say you plug in, can you guys hear me, by the way?
Yeah.
Or did I? Okay.
Yeah.
Okay, it said on my end I cut out, but I didn't. So anyways, do I have okay, I have permission to share my screen. Okay, so essentially, right, if you know how far away, let's say you're trying to local linearize, let's say you have a random function, right, and you want to 3.1, and you want to find the value of that, and you find the tangent line, right? Instead of finding the tangent line, you can also find just the slope of the tangent line, let's say m, right? And you can multiply m, because m is the change in y over one distance in x, right? But let's say you plugged in 3 for your tangent line. What's the distance in x here?
0.1.
So you can just multiply this by 0.1 and get how much it changes from this value to this value. But that's how much it changes. That's not your final answer. So you need to do 0. I should flip that. 0.1 times m plus f of 3 in this case. That's what you can also do that instead of finding the tangent line and then plugging it in. That's just a little. It's a shortcut that also doesn't sacrifice on your conceptual stuff. But anyways, Newton's approximation. You have a function. What does he call the first thing you use? X0? Is that what he calls it? X0?
Yeah.
Okay, so X0, right? And we want to find X1, right? Well, what is this line? F prime of X0 plus, or actually, oops. So let's say first tan line is equal to y minus f of 0, because this point is x0, oops, this point is x0 comma f of x0, right? So y minus f of x0 is equal to m times x minus x0, right? And we know at x1, this tangent line is 0, right? So we can say 0 minus f of x0 is equal to m times x1 minus x0, right? All I did was plug in this point because we know that this point is also on the tangent line, x1 comma 0. So now we divide by m and add x0. So x0 minus f of x0 over m is equal to x1. Boom. And then you just keep doing that. Does that make sense? That's the derivation, if you will. Okay, what did we need to do now? We needed to do differentials.
Yeah.
Okay. Well, I think now it is best to give me a practice problem. Just give me like 1 or 2 of your best ones.
Can you do 11 on
I don't have
like
How the fuck would you?
yeah, send me the picture. Hold on.
what was I was gonna say something else. Okay, so while he's sending me the picture, essentially all you're doing, right, is the chain rule. You know how I showed you all those things where I was canceling out fractions and stuff, right? Or some, and I was canceling out. All you're doing is maybe one. You're doing maybe two or more values, right? You're doing a bunch of these to find some, I don't know, like dA dt or something. You're basically just doing derivative, like fraction multiplication. That's all you're doing with these. I know you guys, we could do one of the cone ones. I remember those. The water. Did he show you guys that? The water and the cones?
No, not yet.
Okay.
Wait, isn't that like how he shows that 3 of the cones equals a cylinder or something?
Yeah, he also, I think that's also how he does it. I might be wrong. Okay. Where
Wait, is there a specific reason that like the when you take a derivative of an area or like the volume of something and you get like the circumference? Like for example, like the volume of a
Oh, okay.
sphere.
Yeah. I had that question too. And the I'm trying to figure out. Okay. So when you're taking the volume, let's say what's the volume of a sphere? 4/3 pi r cubed, right? You're taking the derivative of volume with respect to time. Actually, okay. Honestly, I have no clue. I remember like the explanation I made in my head was volume is some factor times the area. Ooh, I shouldn't use a. Some constant times the area, right? And so when you take, or yeah, honestly, I have no clue. I just remember volume is dependent on area, so the derivative of volume would have area in it, and then you essentially just solve for the area. Honestly, I have no clue about that one.
Like Shara briefly talked to our dude about that. He's like, well, like how 4/3 pi r cubed becomes 4 pi r squared.
Yeah. When you take the derivative, it does work. Honestly, I just have no clue why it works. Why?
It's like something about like surface area.
Yeah. Let me think about this one more time.
Oh, I remember what he said first, but he said pi r squared becomes 2 pi r because apparently you take like all of these little points and then add them up. So then,
Wait. Say that again.
I'm not exactly sure about like what he said, but he said something about like how if it's pi r squared, it becomes 2 pi r, right? So like it becomes the diameter. It has something to do with like adding a bunch of like small points.
Okay. I have a feeling it has to do with okay, here's a roundabout way. I don't have that much time, but I'll try and figure out. If I don't figure this out now, I'll tell you guys the next time we do this, but let's say we have a function for the area. I have no clue what I mean. The function actually yeah, honestly I have no clue. I was about to say something about how yeah, honestly I have no clue. But one thing that does tell you is that actually yeah, I have no clue. I'll just have to I'll figure that out next time. I'll research into that about why surface area is related. But anyways, what question did you want me to do on the in the Discord, the one you sent me? What was the question? 11. Estimate dy given that y is equal to n. Oh, wait, this is exactly what we were talking about in Newton's approximation. So dy by itself is the change in y, right? So he's basically telling you find the change in y from this value to this value. So you do Newton's approximation, and I'll just tell you how to do this. I think you guys can do this on your own. But you can do Newton's approximation. I would have no clue what the function looks like, but you find the function, right? Or you find the function, you plug in, you find the tangent line at pi squared over 6, or 16, whoops, pi squared over 16. You find the tangent line, right? And you see, and you know that the difference in pi squared over 16 and pi squared over 16 times 1 over, or not times, plus 1 over 12 root 2, right? What's the difference between these two x values? What's the distance?
1 over 12 root 2.
1 over 12 root 2. And actually for the tangent line, you only need to find the slope, m, right? Let's slope m, right? And slope is the change in y over change in x, right? So if x changes, let's say m is equal to 3. I have no clue if it is, right? So that means for every, or I'll just keep it at m actually. So for every one unit you go in the x direction, the y value goes up by m units. So how many units does y go up if you go 1 over 2 root 12 units instead of 1 unit? So you multiply the top and bottom by 1 over 12 root 2. And now you'll say whatever this is, right? That's the change in y of this tangent line at 1 if you move 1 over 12 root 2. And I'm assuming it tells you to estimate. That's why it says to estimate dy, because this isn't exact. But that'll give you like the approximate change, right? So your triangle here is 1 over 12 root 2. And then this is whatever this is. I'll call this A for the amount it goes up. Right? Does that make sense? That's the quickest explanation I can give. Is there any questions about that? Does that make sense? Does anyone have any questions about this? I explained it a little bit longer, like 15 minutes ago. But it's just local linearization, right? So you find the tangent line. It's just you find the tangent line, and then you know that the x moves this much, 1 over 2 root 12, between your 2 points. And since you know the slope of the tangent line, you can find how much up it moves in y. So you add a. So your final answer will be a plus the y value of this point. So f of pi squared over 16. Does that make sense?
Yeah. Could you also just solve for like dy over dt from the original like function, and then just multiply both sides by dx? Because you know dx is 1 over 12 root 2.
Yeah, you could do that. Yeah, it's the same thing actually. Yeah. It's actually the same. It's actually the same thing because once you find dy dx, you still can't plug in.
Oh wait, you're right. Yeah.
Yeah, you still can't plug in pi squared over 16 plus 1 over 12 root 2, right? So, but you can plug in pi squared over 16. So you'll just do that and you'll multiply, which is your m, right? That's m, and then you'll multiply by this and you'll get the amount. You still need to add it. You still need to add it though to the y value of your original point that you took the tangent line of.
Wait, could you show what Derek's talking about?
Okay. I'll try my best to show it. I have to go in like, actually.
Oh, my bad.
No, I'll try my best. So, let's say y is equal to x squared, right? And we want to find the difference. Estimate. Let's say this was a function that we couldn't plug in, right? Okay. Actually, before I even start that, I'm gonna erase all this. Okay. So we have y is equal to x squared, right? We have a parabola, and we want to estimate the difference in y. I can't spell estimate. Estimate the difference in y from x equals 1 to x equals 2, right? So we'll find the tangent line, and that is not x squared at all. I just realized because it's origin at the center. But anyways, so we have the parabola, right? And let's say so to estimate it, right? Because you'll actually be doing this with functions you can't plug in easily, but estimate the change in y. So what we'll do is we'll find the tangent line, right? This is like local linearization when we're just approximating. In fact, it is just local linearization. I'm just showing you the shortcut. But anyways, you'll find it at 1, right? So this is 1. You'll find the tangent line at 1. The tangent line will have a slope m, right? And then you'll say, okay, what's the difference between 1 and 2? It just so happens to be 1 this time, right? And what is m? M is the change in y for every 1 unit changed in x, right? Every time x moves forward 1 unit, y moves up m units. And so you multiply it by you multiply the numerator and denominator by the difference. So in this case, it's just 1. But usually you multiply it, let's say the difference here was like 0.5. You multiply it by 0.5, right? And you'd say, okay. And it turns out that was a bad example, right? Let's say this is 2.5, actually. Let me just do that right now. Okay, are you following? I'm talking a bit fast because I have to go soon, but...
Yeah.
Okay. So the distance is 1.5 here, right? So if m moves up this much for every 1 moved in x, how much will it move for every 1.5 moved in x? Because that's how much we move here. So we multiply the top and bottom, and it turns out that it moves 1.5 times m for every 1.5 moved in x. So that's how much, that's the difference between these two values over here, right? That's this difference. But that's not your final answer, because that's just the difference here. You need to add that with the y value over here. You see how this plus this, actually no, wait, you don't need to, yeah, you don't need to add it with that because you're not estimating the y value. That would be local linearization, adding it with this distance over here. But you don't want to do that.
My bad. So it'd be 1.5 m over 1.5 plus 1 if we were like to estimate.
It would just be 1.5 m.
Oh.
Because this is telling you that this is how much it's moving for every 1.5 moved in x. So you only need to know how much it's moving up. Right? This is 1.5 m. So you're adding this to this. You're not adding 1.5 m over 1.5.
And then if you needed to estimate the value, we would add one to it, right?
Yeah, if you needed to
Okay.
actually. So it's literally just local linearization
Yeah.
without that final step, is what he's telling you, to estimate the difference in y. So your answer will be 1.5 m. Does that make sense? I had to talk a little bit faster, but does that make sense?
Yeah.
Okay. I can do one final question.
Wait, could you do 25?
Okay. Is there any topics we haven't done yet? I'd rather do those first, but let's see. 20, oops, that. 25. Use differentials and the graph to approximate, given that g of 3 is 8. So if you want to find g of 2.93, if you know g of 3, you just make the tangent line here, right? And you can just plug in this. But since you're using differentials, this is what I did. Essentially, when they say to use differentials, they're telling you to do this instead, because it's a little faster. So does that make sense? You're doing this thing I just showed you. Right?
So it would be like negative 1/2 over 1, and then you multiply the top and bottom by...
You find the y value, or you find the tangent line at that point, and then you know the difference in x, right? The change in x. And then since you know the slope of the tangent line, you can also find the change in y. And then you just add the change in y to the value of your point, your original point. Does that make sense? Okay.
You could also just plug it straight, or just plug
Yeah,
it
you
into
can
the
plug it
tangent
straight.
line.
You can plug it straight. I find that this is a little bit faster, but and it's conceptually the same. But yeah, you can always plug it straight. Okay. Is there what do we have to do? Differentials? Do you guys have a like? Oh, you guys haven't done applications of differentials, have you? Like like a ladder is falling.
No, that's related rates. That's next.
Oh, that's not okay. I always thought there's differentials. Related rates is essentially differentials, but
Wait. Could I just like touch on like confirm something real quick? So dy is a change in y, right? Dx is change in x.
Yeah.
Delta y is equal to like the function that you get like on one point minus the function at another point, right?
Wait, delta y? Or
Yeah.
delta y is change in y.
Yeah.
All that is it's this delta y, right? So what were you saying delta y is? Let me see.
It's like 1 point minus the other point, like the distance between those.
Yeah. The
Okay.
change in y. And dy is a really small change in y. But it's also, in this case, he's also using it to refer to change in y. These are kind of like people use it interchangeably, even though this is technically a really small change in y. People use it interchangeably.
So they're not equal, right?
No, I mean,
Alright.
people talk about it like it's equal, so I guess you could think of it as equal, but technically these are
consensus is
different.
fine.
Technically,
Okay.
this is a really small delta y, and this is a change in y.
Alright. Thank you.
Okay. So did I cover everything? Is that every? Was there? So there was inverse trig, Newton's approximation, local linearization, and differentials. So that's everything, right? Okay, I can do one last question. Is there a good one that you guys want?
Yeah, there's one that I wanted to go over here. Let me send it in the. All right, I think.
Okay, where do I see it? Oh. Determine the. Okay, angle. Okay, nice. Um, the angle at which. So, I'm not gonna this. I'm assuming because of all the square roots, you're gonna need a calculator for this, but I'll tell you how to do it. So you have y equals x squared over 2, right?
Mhm.
And then you have wait, what is 2 minus 2 minus root 3 over 4 is a positive value, I think. So that would
Yeah.
be that would be more like it would look like this, I think, right?
Yeah.
And to find the angle, you would find the tangent line of this at the
Mhm.
intersection, and then the tangent line of the other function at the intersection. And then okay, here's I think this is the difficult part, finding the angle between two arbitrary. How would I do this? Well, you can make a I'm trying to find an easy way to do this because one way is to like make a triangle off to the side, right? And your triangle would be just points on this, and you would know the distances between your points, right? This would be something, this would be something, this would be something, and then you could use law of cosine to find the angle.
Mhm.
So that's one way you could do it. Does that make sense?
Mhm.
Okay, now I'm trying to figure out if there's an easy way to do this. And honestly, I'm drawing up blank. I think that's the way to do it,
I
right?
can share the work. There's some work. I think I'm not sure if you got it right, but um, this is the work, and I just wanted to
Okay.
understand.
How did you find the angle between the two lines? Did you do?
This is how they did the work.
Oh, okay. So what they did was they found the derivative, and then they found the derivative at the intersection point, which happens to be 1, I guess. Is it? Do they intersect at 1? Do you know that?
Yeah, they did.
Okay.
1,5.
Wait, how do you determine that?
Systems of equations.
Oh, yeah, okay, yeah.
Okay. Angle at which. Wait. That's actually really okay. Wait. That's actually really cool. So what they do is, you know the slopes of these lines, right?
Yeah.
Yeah. You because
Yeah,
you
yeah,
take
obviously, yeah.
yeah. So what you do is you center them at the origin in a separate graph, right?
Mhm.
And then and then you make a triangle, uh, right? You can pick an arbitrary point. You can pick 1 here. I think 1 would be the
Okay.
easiest, right? And then
Okay.
you know theta over here, theta 1 over here, and theta 2 over here, right?
Okay.
And then you
Yeah.
could inverse tangent it because you know the y value here and the y value here, and then subtract the 2. So theta 2 minus theta 1.
Um. Okay. All right.
Because you get the y value over here. Let's say
Wait,
that's
theta 2 minus theta 1 will give you what?
the angle. It'll give you
Yeah.
it'll give you this angle over here.
Okay, yeah. Wait, theta 2 is all of that then?
Yeah, theta
Yes.
2 is this,
Oh, yeah, okay, yeah.
and then theta 1 is the tiny one,
Yeah,
and then theta 2 is this.
yeah. Got it.
Okay.
Wait, so the goal is to find the angle between the two
Yeah.
tangent lines?
So essentially, what they did was after they found the points, they put them on another graph. You see how I'm making?
Yeah.
They put them on another graph like this,
Mhm.
and then they found the angle. Because now since it's on another graph, they can easily do tangent inverse.
Okay.
Here, let me do a better drawing. So we have two lines, right?
Yeah.
Okay. So let's say this is 1 and this is 1. Obviously it's not to scale, but right? And then
Yeah.
that's theta 1. Let's say you can use your calculator. What's inverse tangent? Well, we actually know what that is, like 45.
45.
Obviously this is just I'm just making this up, but
Okay.
and then you find, and then at the same x value, right? So it's still 1. This is I'm pretty sure, yeah, so and then let's say the y value here is 2, right? So now you find tangent inverse of 2, which I have no clue what that is.
Yeah.
So that's theta 2. So that's this whole thing. That's theta 2. And so theta 2 minus theta 1 will be the angle here. That'll be this here.
Yeah. Oh, okay. Yeah.
Okay, yeah, that's pretty clever. Yeah.
Okay. I see. So specifically for this one, they use systems of equations, and then they're trying to find out. Okay, I got it. Got it. Thank you.
Okay, alright, I have to go. So I think I covered everything. Alright,
Right.
I'm ending it.
Thank
Thank
you.
you, sir.
Goodbye.
Thank you so
Thank
much.
you.
Have a great day.
Thanks.